Good afternoon, everybody. Good to see you. Welcome to lecture. First thing I want to do today is tell you about the exam that's coming up on Monday. This is the Canvas page that talks about Exam 3. It has all the Exam 3 information that you'll want to know about it. It tells you the time, the location, the content. It gives you the resources that you're going to be given on that exam. These are attachments that'll be there at the back of the exam stapled to it. You can tear them out and use them if you want or need to, or if you don't need them, that's fine. There are molecules of the day on the exam, and I want to just share with you a new one. You'll recognize the ones that we've talked about so far. We had melatonin when we changed from daylight saving time to standard time. We had acetaminophen, which is over-the-counter pain reliever. We had ethinylestradiol, which was this synthetic estrogen and steroid-type molecule. We had naproxen, which is an over-the-counter non-steroidal anti-inflammatory drug. And then today, this is the new one. This one is triamcinolone acetonide. It's an anti-inflammatory drug, but it's a steroidal type anti-inflammatory. It's really a potent one. It's actually 8 times more potent than prednisone. Let me just blow this thing up so you can get a better look at it. And we appreciate its structural features here. So it's got a whole lot of functional groups in it, but you'll notice the steroid ring system. That's one of the big ones to notice. It's got a ketone here, a hydroxy group there, ketone here, a couple of carbon-carbon double bonds, and a fluorine. And then it's got a functional group that we're going to talk about pretty soon. It's got an acetal in it. If you look at this position right there, that carbon has 2 bonds to oxygen. But it's not a carbon-oxygen double bond. It's just 2 separate oxygens. So this carbon right here is a particular type of one that we're going to learn to identify as an acetal. So the last part of this chapter and the last part of the new content that we're talking about before the exam is going to be about the identification of acetals and their closely related compounds, hemiacetals, and then how they react, how they behave, how they form, how they hydrolyze, and all of that. But this is our new molecule of the day today. It is an anti-inflammatory, very common in a lot of different products. It's sold over the counter in a nasal spray called Nasacort. Just went over the counter not too long ago. It's in a lot of skin creams to treat a variety of skin conditions, so you'll see it in a lot of different places. Well, that's our molecule of the day. I also want to tell you about the survey that we had last time. And the survey was like this. It asked you if you had this phosphorus ylide and this ketone and you put them together, you would get a Wittig reaction, but it goes through one of these oxyphosphatane intermediates. Identify the oxyphosphatane that would be produced in this reaction. So what you need to know is that the mechanism, it's influenced by the partial charges on these species. So the ylide has a lot of partial positive charge on phosphorus and a lot of partial negative charge on that carbon. And the carbonyl has partial negative there and partial positive there. So you put these together in a way such that their complementary charges are associated. And I have a little picture of this in the solution right here that shows how they go together. So they like to line up, so these partial charges are complementary. In other words, the partial negative of O is associated with the partial positive of the phosphorus. The partial negative of the ylide carbon is associated with the partial positive of the carbonyl carbon, and they like to hang out that way, and then they form a 4-membered ring where electrons move, 2 sets of electrons move to give this 4-membered ring with the phosphorus and the oxygen in it. So that was the answer. That was structure letter A. And half the people got it, which was overwhelmingly the most popular answer, and that's a majority of the class, and so I'm pleased about that. Most people got it. Very good. And so hopefully the Wittig reaction chemistry is sinking in. It seems like a good sign. Any questions about the survey? All right, well, we're going to talk a little bit more about Wittig reaction before we move on to talk about acetals. So what I want to do now is tell you a little bit about some scenarios for making double bonds using Wittig reaction and when there's more than one way to do it, sometimes there's a way that's better. In other words, there's sometimes two different routes, but oftentimes one is better than the other. So let's chat about that. So here's a problem, I guess you could say. If you suppose you wanted to make this alkene, and you were gonna make it via Wittig reaction, because Wittig reaction is a good way to make alkenes. There are two ways you can make this. The Wittig reaction makes the carbon-carbon double bond, and so you could have one of the pieces be the ylide and the other piece be the carbonyl species, and that could work two different ways. So I'm going to talk about this as route 1, where this part is the carbonyl part, or aldehyde or ketone. It happens to be a ketone in this place, in this example. And then the other part would be, this part would come from the ylide. So that's route 1. And if it were to do this route 1, the pieces that you would want would be the ketone. In this case, it's a ketone. It would be acetone. And then the ylide that you would need would be this one. So if you put those two together, you would get this. And so that looks pretty decent. I mean, that's not a bad synthesis. That's got a pretty good Wittig reaction. The other option, which we'll look at, is, I'll call it route 2. It would be where this part is the ylide. And this part on the right would be the aldehyde or ketone piece. So you have a choice here. And if we're making that our ylide, the ylide structure would look like this. It would have this phosphorus with 3 phenyl groups attached. And then the bit on the right would have to be an aldehyde piece. And that aldehyde piece would look like this. And so that's like a thinking backwards approach. And so what I should probably do here is make this a nice big arrow, because these retrosynthetic arrows are fat. And what it's saying is that this alkene could come from either this set of reagents or that set of reagents, and these are your two options. So they both look okay. They look fine. I don't see any fatal flaws with these Wittig reactions, but there is an issue if you go back a little further. So what you need to do is decide, how easy is it to make these ylide structures? So we got to go back one step and figure out, what does it take to make this ylide? What kind of phosphonium salt do you need? So to make this ylide, you need a phosphonium halide that looks like that. And then you would deprotonate it by putting in a strong base. In lab, we used sodium hydroxide. You could use that. You could use something even stronger. But you need a strong base, and you would get that ylide. So that looks fine. If we go backwards here and say, what does it take to make this ylide? Where could that ylide come from? You would need this phosphonium salt, where you have the phosphorus attached to that carbon. Okay, so, and same thing, if you put in hydroxide or other strong base, there's a proton there, you'd pluck it off, you'd make that ylide. So far, no big flaws. The problem is when you go back one step further yet. So we're going to go one step further back and say, where's this phosphonium salt come from? And when we do that, one of the things, this is what we finished up with last time, it was the last thing we talked about, that phosphonium salts come from triphenylphosphine and reaction with an alkyl halide. So if you put in triphenylphosphine and an alkyl halide like this, triphenylphosphine phosphorus attacks, you get an SN2 substitution reaction, and you get that product. That looks like a pretty good SN2 substitution reaction, because that's a primary alkyl halide. You just have to make sure your X is a good leaving group, and you'd have a good amount of success with that reaction. Here's where the problem is. If you want to make this one, you need to start with an alkyl halide that is a secondary alkyl halide. This is a primary, this is a secondary, and the triphenylphosphine would need to attack it in an SN2 reaction, and that's more difficult, a lot more difficult, because there's a lot more steric hindrance in a secondary alkyl halide, and SN2 reactions don't work as well. So this step, this step is hard to go from here to here, and the yields might be low. It's not impossible. I mean, you could do it. It's just you would probably have to run the reaction, suffer with a pretty low yield of this. But then once you get that, it'd be okay. So overall, if you had to pick two of these routes, the best one, the one that has the fewest hiccups, would be route 1 is better because the phosphonium salt is easier to make. And the homework for this chapter has a bit of that in there. There's at least one question that is like this. It gives you two different routes and asks you which one is better, or what's wrong with this route, or what do you anticipate being causing trouble. So that will do it. So that's a discussion of Wittig chemistry. How do you feel about Wittig? Do you feel like okay with it? Any questions about Wittig reaction? Okay, then I think we're ready to move on to the next topic. There's a lot of topics in this chapter. We're not going to focus on all of them. We're skipping a lot of stuff. The big thing I want to go into, though, is acetals and hemiacetals, because those are things that appear in a lot of different naturally occurring molecules, lots of different pharmaceuticals. Really important set of functional groups, and we need to chat about them. So here we go. Let's talk about acetals and hemiacetals. Yeah. Oh, I'm sorry. There's a question. Yeah. Hi.
So, is it safe to say that when we're starting with like a ketone or an ylide, we want the most substituted ketone or aldehyde then?
Yeah. Yep. So the question is like if you look at a molecule like this and you want to develop some kind of a shortcut, if you've got one side of it that's more highly substituted, that would be a good choice to have the carbonyl piece be that, because it's hard to make the ylide piece really highly substituted. Yeah, so that's so this is good good strategy. Yeah, thinking about like some of the limitations and how to avoid them. It all goes back to if you pick route 1, you avoid having to do an SN2 substitution reaction on a really hindered alkyl halide. So that's a good thing to try to build into your scheme. So yeah. All right. So let's have a look at this new chemistry. This is addition of alcohols to aldehydes and ketones. Addition of alcohols to aldehydes and ketones. And it introduces two new functional groups, hemiacetal acetals, and then acetals. So here's how it works. If you have yourself an aldehyde or ketone, and I'll pick this one just because it's kind of a nice generic ketone. You could use aldehyde, you could use some different ketone, but some kind of aldehyde or ketone here. When you put this in with a molecule of an alcohol, and for the alcohol, I'm going to use a generic one. I'm going to use OHR just to represent, lots of different alcohols are potentially possible. And maybe what I'll do here is do this one up in a different color. Just to help it stand out. This is an acid catalyzed process, so I'm going to say HA here, acid catalyst. You need that. But what comes out of this then, in equilibrium with the starting material, is this molecule, where we've added one of these alcohol groups. So that's how the equation balances out. You end up with the equivalent of alcohol that's been added to the carbonyl. And so this is called a hemiacetal. You'll learn to recognize these because it's any molecule that has a carbon that has an OH group and an OR group attached to it. So when you see that pattern, think hemiacetal. And the thing about these hemiacetals is that they are in equilibrium when you do follow this a little further. So HA, acid catalyst, catalyzes both the forwards and backwards reactions. Another molecule of alcohol can add, and you get this structure where there are two OR groups that have added. And a molecule of water is lost. So there are your two products. And actually, I think I'm going to draw the water over here so I can make space below this to label what this is. This is an acetal. So we got acetal, we have hemiacetal, and then we have aldehyde or ketone starting material. So if you put an aldehyde or ketone in with alcohol and an acid catalyst, you set up an equilibrium where all of these things are present and they're interconverting, and the equilibrium lies in different places depending on the reactivity of the carbonyl. If it's a ketone like this, the equilibrium is mostly towards the left. It doesn't form acetals all that readily, and hemiacetals are present in very low concentrations. If you get to more reactive carbonyl species like aldehydes, they tend to favor the acetal a little bit more strongly. If you have a really reactive aldehyde, then it favors the acetal by a lot. We're not going to worry about those equilibrium concerns too much, but we are going to talk a lot about the chemistry of these things, like how's the mechanism work, getting from one place to another, how does it work through these, and under what conditions can you make it go to, say, form an acetal if you wanted an acetal, or if you had an acetal and you wanted it to go back to an aldehyde or ketone, how would you do that? And I guess I'll give you a little hint about that. If you take a look at the products, water is a product. And if you think about the Le Chatelier's principle things that you've experienced in other classes and even in this class, if you want to make a reaction go to products, you can remove one of the products. So a common strategy is to get rid of the water. If you remove the water, you can promote acetal formation. And if you want the reaction to favor aldehyde or ketone, you add a lot of this to cause the reaction to want to go back to the left. So these reactions are, you can adjust the position of the reaction based on what you do with the products and the reagents. So we'll talk about that too. First thing though is, how do you recognize these things? Where do they turn up? How can you know where an acetal is? So we're going to practice a little bit with some molecules trying to discover where they are. In other words, given a complicated molecule, can you pick out an acetal or a hemiacetal? And so I'm going to pull up a couple examples of these and we will take a look at them. All right, wow, this is a This is a big one. Let me get the camera focused over here. So don't panic. It's not, it's like, oh no, people are starting to hyperventilate. This molecule it's got a couple of different names. Rapamycin is one it's commonly referred to as. It is an important drug that gets used in situations where rejection of a implanted organ is a big problem. So if you get a liver transplant, it doesn't belong to your body, and so you need to have some kind of drug therapy to prevent you from rejecting it. They also coat this stuff on the surface of stents that get put in to help resist that sort of biocompatibility problem. But it's a big molecule. It has a lot of different functional groups in it. But what you want to do is look through it and see if you can identify them. And some of these functional groups are really familiar. We've got hydroxy group here. There's an ether here. There's an ester here. There's an amide there. Ketone here, ether, ketone, hydroxy. It just goes on and on and on, but there's one spot where there's one of these new functional groups. So look for the carbon that has 2 bonds to oxygen, 2 different oxygens. And if you do that, you can kind of quickly, get through it, and you'll kind of hopefully zoom in on that spot right there. How many, did you get it? Some people got it? Okay, all right. Well, you got to scan it. It takes a while, but yeah, just look for clusters of oxygens in a carbon that's making 2 of them. So that's a hemiacetal right there. And it is an important part of this molecule's behavior, having that in it. I'm going to look for another one here because there's another one. I'll search here. I'll search Wikipedia because they usually have structures, which is something. Spongistatin, it's also got this aldehyde A name. This one's even bigger. Looks pretty wild. It is a natural product. It was actually isolated from a sponge, as you might imagine if it has a name like spongistatin. It is one of the more potent cytotoxic agents that's ever been discovered. In other words, it kills cells really, really well, which you might say, well, that doesn't sound good, except if it had selective toxicity for cancer. And that was one of the things they were looking at with this molecule is, could it be used as a cancer drug? And when I was in my postdoctoral work, I was in a lab where they were trying to make this thing. And they had made it, but they were trying to make it on really pretty big scale, like 5 grams, which doesn't sound like a lot, but this molecule is so potent that would have been enough to do just a whole boatload of studies. But anyway, it's complicated, difficult to make, but it's got a bunch of different functional groups in it, acetals and hemiacetals. So if you go through it just kind of systematically, it is a giant ring system. And so if we want to just start here at noon and go around in a circle and look for them, I don't see any here, but when I get over here, that spot right there, there's an acetal carbon right there. It's a little bit complicated because it's in a couple of different rings, but that carbon has 2 OR groups attached. That's an acetal. Nothing there, nothing there. Get down here. Oh, there's a hemiacetal right there. All right. Looking over here, that is not an acetal. It is sort of similar looking to some of the others, but that's just an ether because that carbon only has 1 bond to oxygen, not 2. This tail over here doesn't contain any acetals. We go up to here, and there's another acetal right there. That's one that's got 2 OR groups in it. So they're common in a lot of different molecules, a lot of different structurally important molecules. So it's an important functional group class, and this is one of the things to get good at is just practicing finding them when you are seeing a molecule. So when you look in the homework, there'll be somewhere it's just like highlight the carbon, the central carbon of an acetal if you see it, or central carbon of a hemiacetal if you see it. And so the size of the molecule really doesn't matter too much. I mean, it takes you a little while to scan it, but I don't think it's inherently more difficult once you know the pattern you're looking for. So don't be intimidated by the size of the molecules. You just have to make sure you don't miss anything, look systematically at them. Make sure you've scrutinized every spot that's got a couple of oxygens in close proximity. So acetals and hemiacetals. Let's talk about how they form, because this is the next thing that we need to understand about them, is where do they come from? We have this reaction that I put on the board over here, and I'll scan back to that just to say another word or two about this. Aldehyde or ketone goes to hemiacetal, hemiacetal then goes to acetal. That's the pattern. It adds one alcohol from the aldehyde or ketone, then it adds the second. If you have an acetal, it can go the other way. If it sheds an alcohol group, it goes from an acetal to a hemiacetal. If it sheds another alcohol group, it goes from a hemiacetal to an aldehyde or ketone. So that's the basic scheme that's going to be happening all the time in these mechanisms. But let's take a look at one here and go through how it works. I'll share with you a simple example to start things off. We'll look at an aldehyde, adding the alcohol methanol. It's one that's easy to draw, which is kind of nice. And hopefully you won't lose track of what's going on. So here's the mechanism. Acetal formation mechanism. So the thing about acid catalyzed mechanisms is you want to get the acid catalyst involved early and often. It's almost always the very first thing that happens, the acid catalyst gets involved. So here's the reaction we're going to look at. We're going to look at propanol, which we just used yesterday in the lab, reacting with methanol. And an acid catalyst, I'm going to just use HA as a short, kind of easy generic acid catalysts, and then we'll talk about like some specific acid catalysts that get used really frequently. So the overall reaction is going to be aldehyde reacting with 2 equivalents of methanol to give propanol dimethylacetal. And a molecule of water. So let's go through it step by step to describe what happens. First thing that happens is the acid catalyst protonates the carbonyl oxygen of the aldehyde or ketone. The thing about this reaction is it's going to involve nucleophilic attack of the aldehyde or the alcohol on the carbonyl. But this is a pretty weak nucleophile. So weak nucleophiles won't attack carbonyl groups on their own. They need a little encouragement, and that's what the acid is for. The acid protonates the carbonyl oxygen and gives this species that has a much more reactive carbonyl, carbon. So when you protonate a carbonyl, you increase its electrophilicity. You make it a lot more positive. So this molecule's got a partial positive charge on the carbonyl carbon. So I wrote it like that so you could, see it. But this one has a way bigger partial charge. In fact, there's a resonance structure that puts a full formal positive charge on that carbon. I'm not going to draw it, but it's there. And if you wanted to draw it, that would help explain how this carbon has just a really big partial positive charge. So it's an activated carbonyl. Now, weak nucleophile like alcohol will attack it, and that's what happens in the next step. And I'm putting double-headed arrows here because all of these steps are reversible. The next step is that an equivalent of methanol acts as a nucleophile and attacks the carbonyl carbon. So here it goes. Comes in like this, attacks there. A pair of electrons get pushed up onto the carbonyl oxygen. And then we have this new species where we've added the alcohol. So we got our H that was there in the first place. We've got the O that came from the methanol. The methanol still has the H that was attached to it originally. It's got a formal plus charge. And over here we have an OH group. This is almost a hemiacetal, but it's not quite finished yet. A minus is the species that you get when the acid donates a proton. The conjugate base of that acid, A minus, is produced. So it's here as well. I didn't draw it in here, but probably I should. There's A minus. And that A minus gets involved in the next step. So it will act as a base and pluck the proton off of that O. So this O now will become neutral. So this process generates a neutral species that has the carbon with the OH and the OCH3. This is the hemiacetal. And this is the halfway point on the way to an acetal. Literally, hemiacetal is halfway to an acetal. And the A minus here grabbed its proton, so we reformed the catalyst in this reaction. It is there, back again, and it can do some more work for us. And it will protonate something in the next step. So here are the options. There are 2 oxygens here that could get protonated by that acid HA. So which one it chooses to protonate is really, it'll do both. So it could end up on this oxygen or that oxygen. If this oxygen were to grab the proton, you'd actually just be back one step. You'd be back where you started with, which is totally possible and happens all the time. But something new could happen if it puts its proton on that oxygen. So if this oxygen were to grab the proton from HA, that would give a species where the OH group has become a good leaving group. It's gotten protonated. It's a water molecule waiting to leave. And we have our OR group here. And it's accompanied by an A minus, conjugate base of the acid. So what happens next is this, and I'll lasso it and just point out this is a good leaving group. It'll leave with a little help, and the way you can show this a couple of different ways. You can just show it leaving without any push from other oxygens. That would give you one resonance structure of the intermediate that you're going to get. Or you could use a pair of electrons on this OCH3 to give it a push. That's, I don't know, there's nothing really better about this approach necessarily, except that it gives a more stable resonance structure. So anyway, I like it. I think the homework in Alex will accept either because they're both technically correct. But what you'll get with this then is a molecule where you've got water gone. Water has left. So H2O is one of the products, and it's left. And there's an A minus here. It's still here, the counter ion. The next thing that happens is another molecule of methanol comes by and attacks here because this has got a lot of partial positive character. That carbon is like a carbonyl carbon that's got a proton on it. If you look back to where we started, I mean, just imagine this molecule with an oxygen here and a CH3 attached to it with a positive charge on oxygen. That's almost exactly like we were at here with the carbonyl group with a proton on the oxygen and a formal plus charge. They're very similar and they react very analogously. So the next thing that happens is another molecule of methanol, I'll draw it this way, comes in, attacks there, and electrons get pushed up onto that oxygen. I'm going to erase the water over here to make some room for this product that I'm going to draw. This gives almost the completed acetal. The only thing that's left to do is it has a proton here that came in with the methanol when the methanol attacked. And that gets plucked off by the conjugate base of the acid that we use, the A-. That comes in and grabs that proton, and that finishes things up. That gives you the acetal that you're looking for, and it regenerates the HA catalyst. So there's the whole sort of thing all at once. And I realize it's a lot of movements of electrons, a lot of intermediates and things, and you're not going to need to draw this from scratch on an exam. I wouldn't expect that level of sort of knowledge, depth of knowledge yet, but hopefully you can follow the arrows and you could supply missing intermediates, or maybe supply missing arrows with intermediates being shown, or missing charges and things like that. So this is the kind of thing that you look at the old exams, you'll see stuff like this. So let's just go through it slowly and talk about it. So first step is activate the carbonyl oxygen with acid to make an activated carbonyl. Then the weak nucleophile alcohol attacks it. Then you get to a point where this is almost the hemiacetal. It just has to have that H removed. Then you're at the hemiacetal stage. Once the hemiacetal forms, it can get protonated on either of the two oxygens. That one, protonating that one gives you the reverse reaction. Protonating this one gives you a species that has water primed to leave. And so it leaves in the next step, and then that species gets attacked by methanol to give this intermediate, which is almost a full acetal, just has to get deprotonated by the conjugate base of the acid, and then you get your acetal. So that's the mechanism. So let's go through some examples of predicting acetal products. Now that you know how they form, the mechanism, let's give you some examples that you can work with to predict. If you saw an aldehyde or ketone and an alcohol, what would you get? So some of these are going to start out a little bit simple, and they're going to get a little bit more complicated. So let's do an easy one, or a pretty easy one first. This one has cyclohexanone, and we'll put in, for an alcohol, I'll put in ethanol. And I'm going to give you, and there'll be an acid, HA. And I'm going to give you a little hint. I'm going to say that water is a product, and I'm going to ask you to predict what is the missing organic product. The fact that you're seeing water should be a clue that you formed an acetal and not hemiacetal. Here's another thing that you can rely on and use. Hemiacetals usually are not stable enough to isolate. They form as intermediates, but they don't really last. So usually you're not going to produce a hemiacetal as a product. There are some important exceptions. Important exceptions exist, But for now, just if you're trying to predict acetal formation or hemiacetal, just know that you're going to go through a hemiacetal intermediate, but it's not going to stop there. Hemiacetal is either going to go back to aldehyde or ketone, or it's going to continue on to acetal. So what you do here is you can think through the entire mechanism, and it's good, I think, to write the mechanism out a few times just with different structures and substrates to make sure you understand what happens. HA protonates the carbonyl, then alcohol weak nucleophile is able to attack it, and you get one of your alcohols added. Then you protonate the OH that forms, that causes it to leave, and then another equivalent of alcohol can attack it. So there isn't two that's written here. This isn't a balanced equation, but you got to know that basically this is one that's going to use excess alcohol. And the thing that comes out of this, besides the water, is going to be this acetal structure where the carbonyl has been replaced by two OCH2CH3 groups. I'm just drawing it as a skeletal structure there. So this is an acetal. And it happens to have the ketone being cyclic. All right, let's take a look at another one here. I'm going to use this ketone, but I'm going to do an alcohol that has two OH groups in it. So you'll see this a fair bit where instead of having alcohols with just one OH group on it, sometimes, actually pretty often, people will use alcohols where there's two OH groups in a single molecule. And this is going to function as the species that's going to add to the carbonyl and take the place of the carbonyl oxygen. When it's drawn like this, it's a little bit tricky to see what's going on. I'm just going to rotate about this carbon-carbon bond, though, and set it up in a way that's going to allow you to probably see it, hopefully see it a little bit more easily. So here's our carbonyl group. What's going to happen here, that carbonyl group is going to get protonated. One of these OH groups is going to attack, and it's going to make a bond here. Then that oxygen gets protonated again, makes it into water, it leaves, and then the other one attacks. And so what you get out after hemiacetal intermediate is a molecule where you've added these two alcohols from the diol, and you make a cyclic acetal and water. Kind of wild, huh? Cyclic. All right, I'm going to show you one that's actually truly wild next. No, this one's interesting. You're going to love it. All right, so that's your acetal carbon, and this bit right here, that came from the alcohols. So if you're trying to deconstruct these things and figure out what carbonyl must this have come from, if you imagine just slicing off the alcohols and replacing the two OR groups with a C double bond O, that gets you back to what the carbonyl group must have been and the two alcohols must have been. All right, so let's take a look at another example over here. So here is a dialcohol. Let me just do a quick structure search here to make sure I've got this structure right. I'm pretty sure I do. This is just old school Wikipedia. ChatGPT would work too, but yep, I got the structure right. Okay, so what happens when you put this in with this and a little bit of acid catalyst? You make a ring, yeah. There's a couple of O's here. I'm just going to draw this formaldehyde structure over here. It cyclizes. That O attacks the carbonyl there. That one attacks the carbonyl there. And you get this species where you make this thing called a methylene dioxy group. It's just basically, it's an acetal. That's the acetal carbon right there, is just an acetal of formaldehyde. And the rest of the molecule just comes along. This is MDMA. Methylene dioxymethamphetamine. That's commonly known as ecstasy. It's a illegal drug, basically. Club drug, rave drug, I guess. I guess that's what the internet says. So anyway, but it fundamentally changes the nature of the molecule. It covers up the two OH groups and converts it into an acetal. All right, let's work on the reverse reactions. What happens if you take an acetal and you want to remove it, hydrolyze it? That's what the process is called. When you take an acetal and you remove the alcohols. Acetal hydrolysis. So here's the overall process. Say you start with an acetal like, I don't know, maybe this one, where you've got a couple of methyl groups, OCH3 groups, and maybe a 1, 2, 3 carbon chain. So that's an acetal. I know because I'm looking at this carbon and I'm seeing 2 OR groups. So if we put this in with water and an acid catalyst, HA, basically what you do is you remove the 2 OR groups and you replace them with a carbonyl where the oxygen comes from the water. So I'm going to draw this in orange just so you can see where everything's coming from. H2O. Carbonyl, and then you get 2 OR groups, CH3, OH. So that's where the atoms come from. And this is just the reverse of acetal forming. If I flip these around and I put these species on the left and these species on the right, it'd be acetal formation reaction. This is acetal hydrolysis. That means cleaving with water, by the way. When you see hydrolyze, cleave with water. There are a lot of hydrolysis reactions out there where basically the water replaces something, cleaves something. And in this case, it cleaves an acetal and gives an aldehyde or ketone and a couple of alcohols. And you could go through the mechanism for this just the same. I'll go through kind of an abbreviated, sort of somewhat quick version of this mechanism. But the first thing that happens is the acid protonates one of the 2 OR groups on the O. It doesn't matter which one. In this case, they're both the same. But that gives this intermediate where one of the OR groups has been made into a good leaving group. So this thing would leave as a weak base, methanol, and that's what happens in the next step. There's an A minus here. So the leaving group leaves, and that gives, as an intermediate, this molecule that's got just one OR group attached. And there's an A minus still here. And we've got an equivalent of methanol that has left. So here's one of the methanols that's come off and come out of this reaction. The next thing that happens is water attacks. So if you're going to do a hydrolysis reaction and you want it to go really, really well, use a lot of water. In that way, the making a huge abundance of reactants here will cause this molecule to get consumed in the equilibrium, the way that equilibrium works, Le Chatelier's principle, and you'll promote the formation of the hydrolysis products. So water acts as a weak nucleophile in the next step. It attacks, because this carbon is like a carbonyl carbon. It's got a lot of partial positive character. And the nucleophile water comes in and attacks there. And that gives, as an intermediate, this species where we have added a water. It's almost at the hemiacetal stage. And when HA grabs, or A minus grabs an H off of here, we're going to get the hemiacetal. So now we're half done with the mechanism. Just erase this methanol here, and we'll go a step further. When A minus grabs its proton, we're left with another HA. We got our catalyst back, and that can protonate something. And it could protonate two different spots. It could either protonate the OH group, like if that oxygen were to grab the proton, it would just give you the reverse product. But it could protonate the other OR group and make it into a good leaving group. And that leads to a new product. So that's what happens next in the mechanism. Is that OR group gets primed to leave by protonation with the acid. So now that this thing is a good leaving group, the OH group can give it a little help, can push a pair of electrons in and push out the other OR group. So this is the second OR group leaving now, and the product of this reaction almost looks like the product. It's just got an extra H on it that needs to come off. And the way that that works is the A minus just comes and grabs that H. And you get to the ketone, and you also get your acid catalyst back. So that is the full process for acetal hydrolysis. Just the reverse of acetal formation, really. I mean, it's the same mechanism, just done in reverse. All right, so we've done a lot of HA drawing, but what are some specific acids that you'll see? This is probably the next most important thing to talk about is if you're going to do it with a real acid, which ones would you use? Well, you want it to be really strong, and if you want the acetal formation reaction to happen, water is a product of that reaction, so you don't want to add a lot of water because water will inhibit the product formation. It encourages hydrolysis, honestly, actually. So what you want to do is, for acids, for HA, select a strong acid with low water content. And here are a few good choices. This is the same collection that you would have seen or you did see last semester when we were talking about dehydration reactions, because in a sense, acetal formation is like a dehydration reaction. You end up spitting water out. The atoms don't all come from one molecule, but it is about producing water. So here are a couple. Sulfuric acid. Sulfuric acid is a very strong acid that contains very little water. So you'll see it most of the time is H2SO4, but that's its Lewis structure. So sulfuric acid is a really good choice. Another one that you've seen before, but maybe not recently, we'll talk about it, it's para-toluene sulfonic acid. This can be made by taking toluene and doing a sulfonation reaction with SO3 and H2SO4. We talked about that in one of our previous chapters when we were talking about aromatic ring chemistry. So that's this is the reaction making this now is something you can do, but it's a strong acid. That proton is really acidic, and it's very similar to the H's in sulfuric acid. If you look at their Lewis structures, they're very, very similar. The whole, like, if you look at sulfuric acid, the S with the 2 double bond O's and the OH looks exactly like the right side of this one. What this one has is a organic part that helps it dissolve in organic solution. So it's a much more organic soluble, really strong acid. This one is called, it's got a bunch of different names. The really long name, I'm not gonna write down even, para-toluene sulfonic acid, but it goes by tosic acid because it's a little shorter name. It also has the abbreviation TSOH. So if you're working in the Alex homework, you might see it drawn in one of those two ways. Probably won't see the full Lewis structure of it because it's cumbersome to draw. One more that would work would be phosphoric acid. It's one that it's a strong acid and has relatively low water content. It's not as good as sulfuric in that sense, but phosphoric H3PO4 would be another choice. And for sure there's others out there as well, but these are the three you're likely to come across. So when you see a reaction that has a carbonyl like an aldehyde or ketone and alcohols, and then you see an acid like HA for generic acid, or H2SO4, or tosic acid, or phosphoric acid, think acetal formation. And if you see an acetal and water and an acid, think acetal hydrolysis. One more thing about this is aqueous acid is sometimes written as simply H3O+. That is acid and water, aqueous acid. And that's the kind of condition that would hydrolyze an acetal. So that's another thing to just be aware of and not get confused by. All right, that is it for today. And we'll talk on Friday. We'll finish up a few things with acetals. We'll review some and get ready for the exam on Monday. So have a good weekend. Or not a good weekend, sorry. Come back on Friday, please. Have a good Thursday.